My name is Jason Scott. I'm an Associate Professor in the School of Chemical Engineering at the University of New South Wales. I'm also Co-Director of the Particles and Catalysis Research Group located within the school. In terms of my areas of expertise, traditionally I've worked in heterogeneous catalysis for various applications. So catalysis or a catalyst is something that you add to a reaction or a chemical process to accelerate that process, so to make it go faster and operate at lower temperatures and pressures. You can also use a catalyst to make your chemical process or your chemical reaction more selective to the product that you desire. But what you need for a catalyst is you need an energy source for it to be activated. Traditionally that's been thermal or heat that's been used to activate the catalyst to drive that chemical reaction. What we do, or what I do, is look at alternative energy inputs. So we look at energy inputs such as light, electricity, plasma, which allow the process to potentially be more sustainable. But what you need to do is you need to be able to tune or design your catalyst so that they can effectively harness those light sources. We spend a lot of time developing catalysts that can do that sort of thing. So take light and use it to drive a certain chemical reaction. In terms of the chemical reactions or the applications, there's a broad range of applications that I've been working on over the years. At the moment, the focus is a lot on carbon dioxide capture and conversion. So taking carbon dioxide from the atmosphere or from an emitter and transforming that into synthetic fuels or chemicals. We also do work with sustainable hydrogen production, splitting water into hydrogen. We also use organics in that as well, so we call that photoreforming. And we also look at processes where we can upcycle waste. So convert a traditional waste stream into a value-added chemical sort of thing, which I guess is to do with the circular economy sort of approach. We take our technology from the lab scale and look to put it into sort of prototype systems. So we've got some sort of demonstrable units that we can show to industry or the community that allows them to visualize and understand the concepts that we're trying to work on. So we'll take some of the materials that we develop in the lab and use that to design prototype systems. So the project that we're working with through the CRC FFS is the manufacture of sustainable construction materials, where we look to utilise agri-waste as one of the resources to produce those materials. SME EcoMag have a process where they can extract magnesium as what's known as a hydrated magnesium carbonate from waste streams that are rich in minerals, including magnesium. And they've got a technology where they remove the magnesium and it comes out as a highly pure carbonate product. The potential exists to lock carbon dioxide up into that product. So your magnesium comes out as a carbonate. You can use carbon dioxide to form that magnesium carbonate, or that HMC. Okay, so then we can take CO2, we can lock it up in the magnesium carbonate, and then we can take that magnesium carbonate and we can use it, we're looking to use it to manufacture construction materials like plasterboard, cladding, cementitious bricks, those sorts of things. So we're looking to develop that approach, looking to understand the synthesis, and when we prepare or synthesize our products, what effect the synthesis processes have on the properties of the final product, say strength, for example. And then we're looking at ways that we can capture carbon dioxide, which don't rely on using existing chemicals, such as sodium hydroxide, potassium hydroxide, which themselves, when they're manufactured, have a significant carbon footprint. So we identified that in some of our earlier techno-economic and LCA life cycle analysis studies. And then also looking to introduce biochar into the final product and seeing what impact that has on the formulation of the product, and also the existing properties when we're looking to, say, apply it as a construction material. In terms of how it can assist with agri-food, well, it's a management of agri-waste sort of thing. So obviously with any sort of agricultural product, you're going to generate a waste. One of the ways that you can manage that waste is through gasification. Take that waste, gasify it, heat it up, burn it, but you also emit byproducts such as carbon dioxide and biochar. So what we're looking to do is take those two byproduct streams, the carbon dioxide, the biochar, mix it with our magnesium from our waste mineral stream, so 3 distinct waste streams, and produce a sustainable construction material at the end. Here at UNSW, we have Natalie Aaron, who's working as a PhD student on those three aspects, understanding the formation of the hydrated magnesium carbonate compounds, the ways in which we can capture carbon dioxide without relying on sodium hydroxide or potassium hydroxide, and also the integration of biochar into the final product and the impact that has on, say, properties such as flammability. But what it's also been is because you've got an industry partner in connection or connected to the project, you've got to balance that fundamental research with what industry needs, or what the final product that industry is looking to develop, sort of thing. And that can be a bit of a balancing act sometimes. Fortunately with EcoMag, they're very open or understanding of the need for the fundamental research, but then also looking to produce a product. And I guess with this project, it was pretty good having EcoMag in there because it was more an exploratory project, I should say, sort of thing. So it wasn't like we have to produce this product with these characteristics. It's like, well, what if we take our waste stream, okay, or our magnesium product from the waste stream, can we get CO2 in there from the environment? Can we integrate biochar, and can we end up with product that utilises all these waste streams in the end of things? So it's been great working with them. In terms of the potential benefits to the construction material, the idea is that you have a sustainable construction material where you've repurposed existing waste streams and integrated them into something that has properties that are comparable to or better than existing products on the market. The benefit of the sustainable materials or repurposing waste is the idea of the circular economy, where you can take traditional waste streams, so you're no longer relying on mineral resources, extracting them from the ground, but you can take a traditional waste stream, repurpose it to produce a product that then avoids extracting minerals. It's better for the environment. If you can do it sustainably, even greater, it's a thing. And then the idea would be that I guess you still have to dispose of that, but then you might be able to take that product and look to repurpose it in some other way.